Assalamu alaikum students, welcome to the class of exercise physiology. We are in week 12 and I'm your instructor Dr. Mohammed Salman Bud, working as assistant professor at University of South Asia. Today we are going to discuss the chapter which is chapter number 10 in your book, and the title of that chapter is respiration during exercise. So we discussed about the circulatory response to exercise in the previous chapter, and the next most important thing to discuss is the respiration, as you need some oxygen and removal of carbon dioxide from your body in order to utilize the body energy in maximum and efficient way. So before we start with this chapter, there are some basic concepts you have to understand. The first is the type of respiration. There is a difference between breathing and respiration. The breathing is the exchange of gases which is going inside the body and coming out of your body. That is known as the breathing. And whereas the respiration, it is more at the cellular level where you are going to utilize the oxygen, and the oxygen will burn the food molecules or glucose molecules to give the energy to the body. So this is the basic difference between the breathing and respiration, and the types are pulmonary respiration and the cellular respiration. The primary function of the pulmonary system is to provide a means of gas exchange between the atmosphere and the body. And it is then I have already said it to you that this will be more or less counted as the breathing or the ventilation, but we are more going to focus in this chapter about the respiration, and we can divide the respiration into the pulmonary respiration and the cellular respiration. The word pulmonary is already familiar to you guys, that it is related to the lungs. So the respiration which is taking place at the lung level will be counted as the pulmonary respiration, whereas the respiration taking place at the cellular level will be called as the cellular respiration. The next thing is the function of the respiratory system, the big picture. The exchange of O2 and carbon dioxide between the lungs and the blood occurs as a result of two processes, the ventilation and the diffusion. I have already explained the ventilation process to you, and the book defined the ventilation is the term refers to the mechanical process of moving air into and out of the lung. This process is commonly called as breathing. So this is the ventilation process. The next thing is the diffusion. So there are some different concepts which you have to understand. The one of them is diffusion. So diffusion is defined as is the random movement of molecules from an area of high concentration to an area of lower concentration. We discussed in our classroom once that there is a difference between the diffusion and osmosis. In diffusion, there is a molecular movement from the higher concentration towards the lower concentration, whereas in osmosis, there is the movement is against the concentration gradient through a semi-permeable membrane. The gases exchange can be summarized into four processes. The first one is the ventilation, that means the moving in and out of the air. The second one is the alveolar gas exchange, the exchange of gases taking place at the alveoli in the lungs. And the third one is the circulatory transport, that means the oxygen which has been absorbed in the blood needs to be transported in the body as well. And then the fourth one is the systemic gas exchange. Once the oxygen reaches to the muscular level or the organ where the oxygen is required, the oxygen needs to be transported at that particular region. So the ventilation or the exchange or the respiration process can be summarized into these four types or in these four processes, starting with the ventilation, alveolar gas exchange, circulatory transport, and systemic gaseous exchange. Then there are different steps which is being depicted in this picture, and if you can start with the point number one in here, it is saying about you are taking inside your oxygen in the body, and there is the atmosphere, there is the oxygen present in the air. You're going to inhale the oxygen in your body. Then the oxygen reaches the surface, and then there will be the oxygen moves into the bloodstream, and then the oxygen will be transported through that blood to the area where it is being required. So then there will be the systemic cells where the oxygen will be exchanged, and then there will be the production of carbon dioxide as you has been utilizing the energy, and the carbon dioxide will be produced as a byproduct. And this byproduct then needs to be removed out of the body, and then the bloodstream is the medium which will remove that carbon dioxide out of the body. And then carbon dioxide will goes into the lungs, and then from the lungs the carbon dioxide will be moved out of your body as well. So this is the process how your air will be moving in and out of the body, and then you are making oxygen availability and removal of carbon dioxide. Then your respiratory system can be divided into two basic types. One is the structural organization, the other one is the functional organization. In the structural organization, it will be into the upper respiratory tract, which will be starting from your nose. Then there will be the nasal cavity and pharynx, and then it will be the larynx, which will be making the upper demarcation of the respiratory system. And afterward, the respiratory system will be counted as the lower respiratory system, and then it will be having your trachea, then there will be bronchus, and then there will be bronchi, and then there will be alveoli in the lungs, and then it will be counted for your lower respiratory system. And for the functional perspective, then there will be one conducting zone and the other one is the respiratory zone. The conducting zone is the zone in which there is only the exchange of gases is taking place, but there is no respiration taking place. Like there is moving of air in and out, but there is no respiration taking place. So that will be known as your conducting zone. But whereas in the respiratory zone, which will be more in the alveolar region, where the oxygen will be utilized and carbon dioxide will be produced, and this region will be called as your respiratory zone. Then there is the anatomy of the placement of the lungs, how the lungs are being placed in your body. And if you can see, like these are present behind your rib cage. And in the rib cage, it will be lying just beside the mediastinum, like the central lining of your chest, the two lungs will be there. And there will be diaphragm which will be supporting the lung from the bottom, and this will be the muscle which will be important for inspiration and expiration, or inhalation or exhalation of the air outside of your body. And then there is one important feature of your lungs is the pleural cavity. The pleural cavity is the cavity which will be lining outside the lungs, and that will be important to maintain the lungs elasticity. If the pleural cavity is not there, the lungs will collapse immediately. And the pleural cavity can further be divided into two layers. The one is the parietal layer, and the other one is the visceral layer. The parietal layer will be the outer layer, whereas the visceral layer will be the inner layer, and there will be one fluid in between the two layers that will be known as the pleural fluid. And this fluid is important to maintain the pressure to keep that lungs open. Otherwise, if that fluid will be not there, the lung. Okay, let's continue with our lecture. And I was talking about the structure of your food pipe. The food pipe is known as the trachea. The trachea is then divided into two bronchi, and then the bronchi will be further divided into bronchioles. Then there will be terminal bronchioles, then there will be respiratory bronchioles and alveolar duct, and then alveolar sac where the gases exchange is taking place. So we discussed about the two zones as well. The first one was the conducting zone, the other one was the respiratory zone. The conducting zone is the one where the gas is taking exchange, the gas is moving in and out only, whereas the respiratory zone is having where the gases exchange is taking place. And now there is in-depth look into this structure as well. In the conducting zone, we have already discussed. This is the conducting zone, which is your trachea, terminal primary bronchus, and there is the bronchial tree, where there is no gaseous exchange is taking place, but the air is moving in and out. And then there is the respiratory zone where the exchange is taking place. There, this is more or less is important, is your alveolus. So these are the alveolus, which is the structural and the functional unit of your respiratory system. And it is said like the respiratory bronchioles are there, which is having a count of 500,000, and there are around 8 million alveolar sacs present in your lung. So this is very much important so that they can take the gases exchange, and they can take the oxygen and remove the carbon dioxide out of your body. And then there are some specialized structures present in that alveoli. There are two important structure. One is the type 1 alveolar cells and the other one is the type 2 alveolar cell. The gaseous exchange is taking place in type 1 alveolar cell, whereas the type 2 alveolar cells are also called as the nursing cells. The most important one in these one are these surfactants, and the macrophages are there as well. But the surfactants are the type 2 alveolar cells. These are important for two reasons. One, they keep the alveoli open. Just like you have seen the phenomena of surfs, it makes the bubbles and it makes the things, or it creates a pressure inside that bubbles to keep that bubble in the form of a balloon. Whereas the surfactants for fulfilling the same function, they are making that balloon-like structure, or they are making that surface tension within the alveoli so that the alveoli should not collapse. And the macrophages are important for your defense mechanism, because once you inhale anything which is injurious to your lung or respiratory system, these macrophages will be there to remove that organ out of your body. Just like sometime it happens, you have inhaled very minute particle which reaches to the alveolar level, then these macrophages will be important to remove that foreign particle out of your body. Okay, then there is the phenomena of inspiration and expiration, which will be take place in relation to the atmospheric and your internal intrapleural pressure. As you know that the atmospheric pressure is of 760 mm of Hg, that is the external pressure of your of air, and that pressure is which is the pressure which will define the amount of inhalation or easiness for you to how to easily inhale the air inside the lungs or not. And then there is two pressure which will be important for inhaling the air inside. One is the intrapleural pressure, which is inside the lungs. Then the second one is the intrapleural pressure. The first one is the intrapulmonary pressure, which is inside the lungs, and the second one is the intrapleural pressure, which is inside that pleural cavity. The intrapleural pressure at the time of rest, it will be 760 mm of Hg, which is equal to that of the atmospheric pressure. So at this pressure, there will be no air moving in and out of your lungs. And at that point, the intrapleural pressure will be of 756 mm of Hg. So there is more pressure inside the lungs as compared to the intrapleural pressure. But once you need to inspire, then there is a decrease in the intrapulmonary pressure and in the intrapleural pressure. So the atmospheric pressure remains the same, and then it will be 760 mm of Hg, whereas your intrapulmonary pressure will become 757 mm of Hg, and then there will be intrapleural pressure will decrease to 754 mm of Hg. So there is a universal rule, as we discussed about the diffusion as well. From the higher concentration towards a lower concentration, the air molecules will move. So the pressure outside is higher, the pressure inside is lower, so the air will move from outside to inside. Then there will be expiration. Then you are going to expire the air. For that reason, the intrapulmonary pressure has to be greater than the atmospheric pressure. So the atmospheric pressure, you already know, it is 760 mm of Hg. So your intrapleural pressure will become 763 mm of Hg. So that will facilitate the movement of air from the lungs to out of your body into the atmosphere, because the atmospheric pressure is lower as compared to the intrapleural intrapulmonary pressure. Then there are the muscle which will be responsible for inspiration and expiration. The inspiration process is more or less actively performed, whereas the exhalation process or expiration process will be passively performed if you are not going to make any forced expiration. For the inspiration, the muscle important for the inspiration are sternocleidomastoid. There are the scalene muscles. There are external intercostal muscles. There are pectoralis major muscle, intercostal muscles, and diaphragm. These are the muscles which are important for the inspiration of the air inside the body. and they will be making the lung space, or they will be making the rib cage open, so that there is the negative pressure generated within the in the rib cage, so it will facilitate the air to move from the outside towards the inside. Whereas the force expiration muscles are the internal intercostal interosseous part, which will be making some effort in order to compress your rib cage, and then there will be increased pressure inside the rib cage to make the air exhale out of your body. Then the moving of air inside and outside will depend upon the pressure difference between your atmospheric pressure and your lung pressure. As we have already discussed this phenomena in the previous slide, that the P1 is your partial pressure of the lung, partial pressure of the atmosphere, and then the P2 is the partial pressure of your lungs. So if the partial pressure of the lungs will be higher, then it will be facilitate the expiration, whereas if the atmospheric pressure will be higher, it will facilitate the inspiration process. And the second important thing is the resistance of your inspiratory tract. If there is higher resistance, then it will be difficult for the air to move in and out of your lungs. If there will be less resistance, which can be created by the trachea itself as well, because there are some ciliary movement of the cilia, there can be mucus production, and these kind of things will make the resistance increased. So increase in the resistance, there will be less airflow, and if there will be the greater difference between the atmospheric pressure and the pulmonary pressure, then the airflow will be higher as well. The primary factor that contributes to the airflow resistance is the pulmonary system in the diameter of the airflow. Higher the diameter, then there will be the greater airflow will be. The less the diameter, then the less will be the airflow as well. And then there are some important terminologies and variables which you need to study in order to study the pulmonary ventilation. The first one is the symbol is V, which is denoted for volume of gas. V means volume per unit of time, generally 1 minute, like how much volume of air is moving in and out of your lung in 1 minute time. And then there are some other variables or symbols such as T, which is denoted for the tidal volume, D, which is for the dead space, A for the alveolar, I for inspired, and E for expired respectively. So these are the symbols which you have to understand, and whenever you are discussing about the respiratory system, these symbols will be of great importance for you. And then there is the volume per unit time. This is defined as that the amount of gas ventilated per minute in the product of the frequency breathing and the amount of gas moved per breath. So before understanding the phenomena or the concept of volume per unit time, you have to understand the concept of tidal volume. The tidal volume is the volume of air you are making in and out in one inspiration and expiration, and that is equals to 500 milliliter. And if you want to study, or if you want to calculate the volume per unit time, then you have to multiply that one time movement of air in and out multiplied by the number of breaths you are taking in 1 minute. It is said that you are normally having 15 to 18 breaths per minute. So you can multiply 18 with the tidal volume, then it will give you the volume per unit time. Then there is one more important concept, which is the anatomical dead space. It is that space which is the area inside your lungs which remain unused. And that unused ventilation area is called as the dead space, and the space it occupies is known as anatomical dead space. And the volume of inspired gas that reaches the respiratory zone is referred to as the alveolar ventilation. So the first we have to understand the anatomical dead space. So your air is going inside the lung, and not whole part of the lung is actively involved in making the gaseous exchange. So air will trap into that area of the lung where there is in a way no blood supply, or you can say like there is no gases exchange take place. So that area of the lung will be called as the anatomical dead space area. But the area in which there is the respiratory exchange is taking place will be called as alveolar ventilation area. And then you have to concept of spirometry. Without this one, you will not be able to understand how your lung is basically functioning. It's just like it is as equal important as you are going to measure the blood pressure by sphygmomanometer. So this is the thing, like you are going to measure the different type of volumes, different type of capacities of your lungs, and the process of measuring that one will be known as spirometry. And this is the most important table, which I will say will be important for your final exam perspectives as well. So you have to understand the concept of the volume and the capacity. The volume is here is denoted by these wave-like structures, that the volume which you are making in and out, and the capacity is the strength or the ability of the lungs to hold that amount of volume. So one is the tidal volume we discussed, is the amount of air you are moving in and out. So this is 500 milliliter. If you can say it is around 2500 milliliter to 3000 milliliter, the volume will be fluctuating. In this one, it will be 500 milliliter, and this will be known as the tidal volume. And then if you can make any kind of expiratory force expiration, then there will be one volume. This graph is showing, downward graph is showing this area of expired, forcefully expired area, forcefully expired volume. And then there will be some residual volume left, even if you have made the force expired volume, but there will be still some residual volume left in your lungs. And I will explain this concept in the next table with reference to the values as well. So this is the tidal volume. It is equals to 500 milliliter, and it is defined as the amount of air inhaled or exhaled in one breath during quiet breathing. It is important that you are breathing quietly as well, like you are not doing this in any strenuous activities or any sports activities. And then the second one is the inspiratory reserve volume. It is abbreviated as IRV. It is equals to 3000 milliliter. And then the amount of air in excess of tidal volume that can be inhaled with maximum effort. So sometimes it happens like you can inhale more than the normal amount of air, just like you make this kind of actions and then you are inhaling more than the amount of air you can normally inhale. So this is known as the inspiratory reserve volume. And then there is expiratory reserve volume. It's the amount of air in excess of tidal volume that can be exhaled with the maximum effort. So this is the opposite to the inspiratory reserve volume. Just like you have forcefully inspired, now you are making forcefully expiration of the air. So this is more than the air you are normally exhaling out of the body. But still making this force expiration, there will be an amount of air that will remain within your lungs that will be known as the residual volume. And it will be defined as the amount of air remaining in the lungs after maximum expiration, that is the amount of air that can never be voluntarily exhaled. So this is the amount of air you cannot exhale out of your lungs. And then if you will combine these different values, the values of the volume, then it will gives you the different values for the capacities. So you can say that in order to measure the capacities, you have to merge different volumes together. So the vital capacity is equals to 4700 milliliters, and it is defined as the amount of air that can be forcefully exhaled following a maximum inspiration. So this can be abbreviated as ERV. VC is equals to ERV is the expiratory reserve volume plus the tidal volume plus the inspiratory reserve volume. So when you will combine these three volumes, it will gives you a value of 4700 milliliter. And then there will be the inspiratory capacity. The inspiratory capacity is equals to 3500 milliliters, and it will be equals to the tidal volume plus inspiratory reserve volume. And then there will be the functional residual capacity, in which your air is making the movement most of the time, and it is equals to 2500 milliliter, and it's the amount of air remaining in the lungs following a normal expiration, and it is equals to the residual volume plus expiratory reserve volume. And then the total lung capacity capacity means the lungs has a total capacity of 6,000 milliliters. You can say it is equals to 6 liter as well. So your lung is having a total capacity of 6 liters or 6,000 milliliters, and it is defined as the maximum amount of air in the lungs at the end of maximum inspiration. It is equals to the reserve volume, the residual volume plus the vital capacity. So you can say, in other words, it is a sum of all the volumes in the lungs will be equals to the total lung capacity. And you can easily differentiate between a healthy person and a healthy person, just like measuring these capacities. And if you can see in here, there are two people having two different graphs in here. One is the COPD, which is the coronary, which is the pulmonary disease, chronic obstructive pulmonary disease patient, and it is having a vital capacity of 3 liters only. And the forced expiratory volume is equals to 1 liter only, whereas the forced expiratory volume for a healthy or a normal person is 4 liter, whereas the vital capacity for that one is the 5 liters. So you can say that the normal person is having more capacity as compared to the coronary obstructive pulmonary disease patient, COPD patient. And then this graph will explain you each and everything, that the capacities and the performance of the lungs is deteriorating in the COPD patient as compared to the normal patient. And then there is an important function of making the diffusion of gases, how the gases is making the diffusion inside and outside of the lung and in the blood itself. And it can be understood by the Dalton's law, which define that the total pressure of a gas mixture is equals to the sum of pressure that each gas would exert independently. And if you know that the air is a mixture of different gases, and these different mixture of gases making an atmospheric pressure of 760 mm of Hg at sea level. And in that 760 mm of Hg, the percentage of oxygen is 20.93, nitrogen is having 79.04, and carbon dioxide is 0.03. And that gives a fraction of 0.2093 for oxygen, 0.7904 for nitrogen, and 0.003 for carbon dioxide. And if you want to measure the partial pressure of oxygen, then it will be the formula which will be making in here, that you are going to multiply the total atmospheric pressure with the fraction of oxygen, and it will give you the partial pressure of oxygen. The partial pressure of oxygen means that in this 760 mm of Hg, this is the pressure which is being generated by the volume of oxygen in 765 mm of Hg. So in 765 mm of Hg, the partial pressure of oxygen is 159 mm of Hg in the atmosphere. And now we are going to utilize this value in order to understand the phenomena of inspiration and expiration in the lungs. So if you are going to understand this process in relation to these partial pressures now, so if you can see in here, the partial pressure of oxygen is 159 in the atmosphere when you are going to inspire, and the partial pressure of carbon dioxide is 0.3 mm of Hg when you are going to inspire. So once you inspire, the partial pressure of oxygen is decreasing in a way because it is being utilized. When it reaches to the alveoli, the partial pressure reaches to 104 mm of Hg. But as you have already utilized some of the oxygen and carbon dioxide is being produced, so there is excess of carbon dioxide in the lungs. So in the alveolar air, the carbon dioxide pressure will be 40 mm of Hg. And moving further into the bloodstream, when it reaches to the heart, then you will be having a partial pressure of oxygen 95 mm of Hg, whereas the carbon dioxide pressure will be 40 mm of Hg as well. You might have seen any cardiac patient or heart patient, or you might have seen any patient to see the partial pressure of saturation of oxygen as well sometimes. So they will be having one device and on their finger, and then it will be giving you the saturation rate of oxygen, or sometimes the partial pressure of oxygen as well, and that will be equals to the 95 mm of Hg. And this 95 mm of Hg will be utilized in order to transport the oxygen to the systemic circuit, and then it will be given to the muscles or any organ where it will be required, and then the pressure of oxygen will decrease drastically, and it reaches to 40 mm of Hg, and the pressure of carbon dioxide will reach to 46 mm of Hg. And from here, then there there will be removal of carbon dioxide and there will be a little bit oxygen left, but then the blood will be called as deoxygenated blood, and whereas this red portion will be called as the oxygenated blood in here. And from here the blood will be pumped back into the lungs, and air will be expired from the lungs, and then the expired air will be having a partial pressure of oxygen 116 mmHg, and there will be partial pressure of carbon dioxide 40 mmHg. Again, here the carbon dioxide pressure remains 40 mmHg, but the partial pressure of oxygen increases because of the availability of oxygen inside the lungs when you are inspiring. So that will saturate your expired air as well a little bit, but the partial pressure still is lower than that of 159 mmHg, which will make it easier for the oxygen to be expired out of the lungs. Then the next concept is the blood flow to the lungs, like how your blood will be having the circulatory system. The pulmonary circulation is the low pressure system in which with a rate of a low pressure system with the rate of blood flow equals to that in the systemic circuit. And the circulation in the lungs is known as the pulmonary circulation. You already know this concept. And then they will be in a standing position. Most of the blood flows to the lungs is distributed to the base of the lungs due to the gravitational force. So there will be the gravitational force, which will be of great importance when you will be like in a standing position. Then there will be more blood pooled in the lower portion of your lungs as compared to the upper portion of the lungs. This concept is very important because we are going to discuss this concept in the coming lecture or in the coming slides as well. So this is important that once you are standing, then the blood will be more pooled in your lower portion of the of your lungs as compared to the upper portion of the lungs. And then this is the complete circulatory system of your lungs, and we have already discussed in the previous chapter when we were discussing about the circulatory system during the exercise. But if you know it from that chapter, that your left side of the heart is oxygenated one and the right side of the heart will be the deoxygenated one. The right side will be collecting the blood from all part of the body, from the inferior and the superior vena cava, and then it enters into the right atrium. From the right atrium, it enters into the right ventricle. From the right ventricle, the blood is being pumped to the lungs by the pulmonary artery. And in the pulmonary artery, the blood gets oxygenated and it will return back by the pulmonary vein into the left atrium, and from the left atrium it enters into the left ventricle, and then it will be circulated in the whole body to supply the oxygen to the muscles and to the organs, and then it will be returned back again. Then this will be making a complete system which will be known as the pulmonary circulatory system and the systemic circulatory system, and we have discussed it in great detail in the previous chapter, so I will not spend much time on this one. And then there will be the blood flow in relation to the rib number, starting from the rib number 5. That means that is the lower number of your ribs. So there will be a higher amount of blood flow. As we discussed in the previous slide, that the pooled in the lower portion more. So once you are in a standing position, the blood will be more pooled in the lower portion of your lungs. So once you are moving upward in the rib cage towards the 1 or 2 ribs, then the blood flow will be decreasing, and you can say it will be making an indirect relationship. And it is explained that the regional blood flow within the lung, note that there is a linear decrease in the blood flow from the lower region of the lung toward the upper region. So there is an indirect relationship. As you are moving upward in your rib cage, the blood flow will decrease. Then the next concept is the ventilation to perfusion relationship. This relationship is important in order to understand like how good your blood is getting oxygenated. So ventilation and perfusion relationship means that the oxygen is coming from one way, and then there is the blood which is present in the lungs, and how these two things will overlap each other. And this ventilation perfusion relationship will define like how good your oxygen, the blood is getting saturated. So this is defined in your book is the efficient gas exchange between the blood and the lung requires proper matching of the blood flow to the ventilation, called as the ventilation perfusion relationship. As I have already explained, like how the blood is coming and how the oxygen is available in there, that will define how good your blood will be saturated. The ideal ratio, it has to be 1. It means like the amount of blood which is coming and the amount of air which is coming from the other side are of equal amount. So once you are having equal amount in your numerator and denominator, then the perfusion value, the ratio value will be equals to 1. So once you are having ventilation perfusion relationship value equals to 1, that means your blood is getting good perfusion, or your blood is getting highly oxygenated. So you will be having more oxygen in your blood as compared to the value which will be lower than 1. So this will be defining about the different ventilation perfusion rates, and this is saying in here, if you are having a higher value greater than 1, that means you will be having more oxygen as compared to the blood. And if you are having a higher value, if you are having a lower value than 1, that means you are having more blood as compared to the air. And if you can see in here, the ventilation is zero point 0.2 liter per minute, and the blood flow is 0.07 liter per minute in the apex of your lungs. So once you will divide this 0.24 by this 0.07, you will get a ratio value of 3.43, which means there is more ventilation as compared to the blood flow. And then there will be in here, if you can see in here at the base, there is less oxygen and there is a higher amount of blood. So in this sense, you can say that if you will divide 0.82 by 1.29, you will get a ratio value of 0.64, which will be depicting that your blood flow is higher as compared to the ventilation in this region. And the next concept is transport of oxygen in the blood. And it is said that, or you have already known this phenomena, like more than 99% of oxygen in the blood is being transported by combination to hemoglobin. The hemoglobin is a special protein in your blood, which is important for binding the oxygen molecules, and then it will transport the oxygen in your body. And then the next thing is about each gram of hemoglobin can carry around 1.3 milliliter of oxygen. So this is important that your hemoglobin will be having this capacity, and you will be having sufficient amount of hemoglobin in the body to transport the required oxygen level. Okay, then the next thing is oxygen hemoglobin dissociation curve. Your oxygen is getting combined with the hemoglobin, but it will depend upon the partial pressure of oxygen. As the partial pressure of oxygen is declining, as you have seen in the circulatory system and the partial pressure slides in the previous slides, and the partial pressure of oxygen is on decline, and then at a certain point, then your oxygen will dissociate very rapidly. And it is defined in your book that the quantitative relationship between the partial pressure of oxygen and binding of O2 to the hemoglobin in blood is called oxygen hemoglobin dissociation curve. And the combination of oxygen with the hemoglobin in the lungs is called as the loading, and then there is the release of oxygen from the hemoglobin at the tissue is called as unloading. So there are now two things which you have to understand, that the partial pressure of oxygen will define that how much your hemoglobin going to associate the oxygen with it. And the combining of oxygen with the blood will be known as loading, and then dissociating of oxygen from the blood will be, or from the hemoglobin will be known as unloading. And this is very important graph in order to understand this concept of loading and unloading of oxygen, and combining and releasing oxygen by the hemoglobin. If you can see in here, this is the partial pressure of oxygen, which can take place to 100 mm of Hg. And this is a percentage of oxygen combining the hemoglobin, and this is the percent of oxyhemoglobin saturation. That means how much is the hemoglobin is getting saturated. And then this is the oxygen content, which is the milliliter oxygen per 100 milliliter of blood. So you can say like this is giving you the amount of oxygen loading and unloading in here. This is the amount of hemoglobin saturation in here, and this is a partial pressure of oxygen pressure of oxygen in here. So starting from the arterial blood in the arteries, as you know, like there is more oxygen and the blood is saturated one, the partial pressure of oxygen is 100 and the oxyhemoglobin saturation is also 100, and this is the process of full loading in here. And afterward the oxygen is start dissociating from the hemoglobin and the partial pressure is decreasing, and then there is a threshold reaching at the point of 15% of oxygen content or around the 75% of oxyhemoglobin saturation or at a partial pressure of 40 mm of Hg. So in these circumstances, you can say like if there is the oxygen content is 15, there is oxyhemoglobin saturation is 75% or partial pressure is of oxygen is around 40%, you can say that this is the process of unloading. Then you can say that this will be the start of the venous blood. So you can say the portion from here to here is the oxygenated blood and the portion from here to here is the deoxygenated blood. So this is very much important to understand the concept of saturation of oxygen. And there is very important phenomena of the location of this point. If this graph is moving towards the right side, that means there is the less capacity of oxygen to stay associated with the hemoglobin, and there will be a higher capacity of oxygen to dissociate even at a higher partial pressure of oxygen. But if this graph is moving towards the left side, that means there is a higher capacity of the oxygen to stay associated with the hemoglobin. So moving the graph toward the left side will be somewhat beneficial, whereas the moving the graph towards the right side will be something which is not good for your participant. And there are the factors which will determine the direction, and there is the factor which will be the partial pressure of oxygen in the blood. There is the affinity or the bond strength between the hemoglobin and the oxygen, and then third one is an increase in body temperature and a reduction in blood pH results in a right shift in the oxygen hemoglobin dissociation curve and a reduced affinity of hemoglobin for the O2. So this is something very much important that if you are going to understand this thing, it will be important for you guys that if the graph is moving towards the right side, it is not good for the person, and if the graph is moving toward the left side, it is beneficial. And there are some different factors which will be affecting this oxygen hemoglobin dissociation curve. The first one which we'll be explaining in here is the pH of your blood. The normal pH of the blood is ranging between 7.35 to 7.45. So if you are having a pH on average is 7.40, that will be the normal one, which is in the center in here for you guys. So this is the normal pH of the blood, and in here the graph is following the normal pattern. But if the pH is decreasing, then it will be reaching to 7.20, that the blood is getting more acidic. Then the graph is moving towards the right side. There is the affinity of your hemoglobin oxygen association is decreasing. And if your blood is getting alkaline, then your graph is moving towards the left side. That means your affinity for oxygen to stay with the hemoglobin will be increased. So this will be good in this case that your blood is having a little bit alkaline in nature as compared to the acidic in nature. And the book says about this graph that the effect of changing blood pH on the shape of the oxygen hemoglobin dissociation curve, a decrease in the pH, increased acidity results in a rightward shift of the graph, which is known as the Bohr effect. Whereas an increase in the pH decreased in the acidity will result in the leftward shift of the graph. That means there is increase in the affinity of oxygen with the hemoglobin. So after the oxygen affiliation or affinity with the hemoglobin, which is being affected by the pH, the next important thing which will affect your affinity of oxygen with the hemoglobin will be your temperature. So there will be a different affinity for oxygen and hemoglobin at different temperatures. So this will be including in here, which will be explaining that at a temperature of 37 Celsius, the affinity will be following the normal pattern. And if there is an increase in the temperature, it is about the air temperature or the blood temperature. So if there is an increase in the blood temperature or the core body temperature, then there will be an increase, there will be an decreased affinity of oxygen to be staying associated with the hemoglobin. And then there is a lower body temperature, then it will be that your oxygen is staying more with your hemoglobin, so there will be an increase in the affinity. And the book explained this graph, the effect of changing blood temperature on the shape of the oxygen hemoglobin dissociation curve. An increase in temperature result in a rightward shift in the graph, as in this case that is showing in here for the 42 Celsius, and the graph, while a decrease in the blood temperature results in a leftward shift in the graph, as it is being showing in here, which is the 32 Celsius for your blood temperature. And then the next important concept is how your oxygen is being transported. The oxygen is being transported by the hemoglobin, as you have seen already. But there are one more important protein which is present in the muscle, which is known as the myoglobin, which will be responsible for transporting the oxygen as well in some circumstances. And the myoglobin is having far more affinity for the oxygen as well. So it is said like the myoglobin is an oxygen binding protein found in skeletal muscles, and the myoglobin is similar in structure to the hemoglobin but is about one-fourth the weight. So it is lighter than the hemoglobin, but the myoglobin has a greater affinity of oxygen than the hemoglobin, and the myoglobin oxygen dissociation curve is much steeper than that of hemoglobin for partial pressure of oxygen values below 20 mm of Hg. I will show you this graph in the next slide, and it will be more clear for you what it is saying in here. And then the myoglobin oxygen stores may serve as an O2 reserve during the transition period from rest to exercise. So this is a graph I'm talking about to you guys, and here you can see in here that this is the normal graph we have, which is the oxygen hemoglobin dissociation curve graph. And we have already discussed that for that one, the critical value of partial pressure of oxygen is 40 mm of Hg. But at myoglobin level, if you can see in here, the saturation of oxygen in here with the myoglobin at a partial pressure of 20 mm of Hg is still greater than 85% in here. So, but in here, if the partial pressure is decreasing, then there is decrease in the saturation with the hemoglobin. But with the myoglobin, the partial pressure has decreased to 20 mm of Hg, but the saturation is still quite high in here. Okay, continue with this lecture. Now we are going to discuss about the transportation of carbon dioxide in the blood. The carbon dioxide, which will be counted as the waste product in your body, will be transported through different mechanisms. The one is the dissolved one, in which the carbon dioxide will be transported about 10%. Then there will be combination with the hemoglobin, which will be dissolved, which will be transported around 20%, and then in the form of bicarbonate, which will be the 70%. So carbon dioxide will more transported in the form of bicarbonate ions, and this is the major mechanism by which the carbon dioxide will be transported. So this picture is explaining about this phenomena. If you can see in here, HbCO2, this is a combination of carbon dioxide with the hemoglobin, which is one of the type for removal of carbon dioxide. The second is the dissolved carbon dioxide in here, and the third one is this bicarbonate ions. So these are the three mechanisms which will be making the transportation of carbon dioxide in your body. And then there will be the ventilation and acid-base balance. And if you can see in here, if you are having a higher amount of carbon dioxide, then it will be making more amount of bicarbonate ions and hydrogen ions. And higher the amount of carbon dioxide will increase the amount of hydrogen ions and bicarbonate ions. And you understand the concept of pH. That means higher the pH will be higher, will be having a higher amount of hydrogen ions. So once the pH will decrease, that your blood is getting acidic, then that means there is there is the dissociation of the oxygen more easily from the hemoglobin as well. So this is very important phenomena. Like if you are having a higher amount of hydrogen ion and bicarbonate ion, then there will be a difficult scenario for the athlete to perform exercise. And these are the changes which will happen in your body when you will be performing the exercise. Starting from rest, there will be a little decrease in the partial pressure of oxygen, but it will retain the partial pressure after some time. There will be a slight increase in the partial pressure of carbon dioxide, but it will retain the partial pressure after some time. And then there will be the ventilation frequency, which will increase dramatically in order to maintain these two partial pressures. So your respiratory, or the frequency of respiration or breathing, will increase in order to maintain this partial pressure of oxygen and carbon dioxide. Then there is the exercise in the hot environment. There is no difference being measured when you are performing in hot environment. The carbon dioxide partial pressure will remain the same. The only difference which will make in the hot and humid environment is the difference in the ventilation rate only. Your ventilation rate will increase in hot and humid environment in order to perform the same type of exercise, but in the cold environment your ventilation rate will not increase that dramatically. This is for the incremental exercises, and it is making a comparison between the untrained athlete and the trained athlete. In the untrained athlete, the dissociation of oxygen is very slow. But in the trained athlete, once it starts the exercise, the dissociation of oxygen is high, and it makes it easier for the athlete to have excess of oxygen availability. So this dissociation in this term is in terms of availability of oxygen to the muscle in order to perform better exercise. The pH of the blood is increasing after some times very quickly for the untrained one, whereas the pH will decrease very slowly for the trained athlete. And then there is a ventilation. You will see in here that the untrained will make the breathing frequency very high after a short span of time of work rate, whereas the breathing pattern will not increase very easily in the trained athlete. Then the last concept of this chapter is about the control center of the ventilation. It will be in your brain, and then there will be the pons and medulla oblongata, which will be the areas which are responsible for this control center of your respiratory system. And these are present in your brain stems, and these are the pneumotoxic centers, and they are the caudal pons, and they are the retrospoid nucleuses, which are responsible for controlling your breathing activities. And they are having different inputs, and their inputs are from the neural perspective as well. There will be the neural innervations in your in your vessels, and there will be the hormonal changes in response to the carbon dioxide concentration increase and in terms of hypoxia. So these are the two types which will give the signals to your brain in order to control your breathing pattern. And then there will be the humoral chemoreceptor. The respiratory chemoreceptors are classified according to their location as being either in the central chemoreceptor or in the peripheral chemoreceptor. Either they are present in the brain itself, or either they are present in the body. So these are the pictures which will be depicting about the central chemoreceptor, which are present in the medulla oblongata itself, or they are the peripheral one, which are present in the common carotid arteries or arch of aorta. And then there will be the ventilation in relation to the arterial partial pressure of carbon dioxide. As the partial pressure of carbon dioxide is increasing, your ventilation rate will also increase, and this will be making a linear direct relationship. As the number of, or as the partial pressure of carbon dioxide is increasing, then there is increase in your respiratory rate for performing the activity as well. And in relation to the partial pressure of oxygen, then if your partial pressure of oxygen is decreasing, then there will be decrease in your then if the partial pressure of your oxygen is decreasing, then there will be an increase in your respiratory rate. So it is said like around 65 Hg, that will be the state of hypoxia, that you are lacking oxygen in the body. Then you will be start making the fast breathing pattern or brisk breathing pattern, like you will be making more inspiration and expiration in order to meet this hypoxic state of the body. So then this is the picture which will be giving you the idea about different type of receptors to give the input to the respiratory control system to regulate the breathing during exercise. So we talk about the chemoreceptor which are located in the medulla oblongata, which will be sensitive to increase in carbon dioxide partial pressure. Then there are the common carotid arteries, which will be sensitive to increase in the partial pressure of oxygen, carbon dioxide. They will be sensitive to the decrease in the pH in terms of if your blood is getting acidic, and then it will be also sensitive to the decrease in the partial pressure of oxygen. And then there will be the aortic bodies that will be sensitive to increase in the partial pressure of carbon dioxide, and there will be decrease in the pH. They will be also monitoring this change in the blood as well. And then there will be the muscle mechanoreceptors. They will be sensitive to the muscle contractile activity. If you have increased the contractile activity, that means it will send the message to the brain to increase the respiratory patterns as well. And then there will be the muscle chemoreceptor, that you will be having a decrease in the pH in form of the lactic acid accumulation in the muscles and increase in the in potassium in there. So these two changes will give the signal to the brain, and then in response to these changes, these changes will be brought by the breathing control system in order to maintain the carbon dioxide and oxygen values in the body and to perform the efficient exercises for you guys, for the athlete. So this is the chapter, and this will be giving you the summary now about for controlling the respiratory system. So if you can see in here, this is the respiratory control center, which is present in the medulla oblongata. You will be having the peripheral chemoreceptors. You will be having high brain centers, which will be sending the message to that respiratory control center. And then there will be the chemoreceptor and the mechanoreceptor, which will be providing the signals to the respiratory control center. And in response to that one, the respiratory control center is sending the message to the respiratory muscles to perform the necessary function in order to increase the ventilation rate. And then there will be, does the pulmonary system limit maximum exercise performance? This is very important slide. After reading this lengthy chapter, it is said at the end of your book that the pulmonary system does not limit exercise performance in healthy young subject during prolonged submaximal exercises. But this is for the submaximal exercise. This is not for the maximal exercise. But if you want to enhance the performance of an athlete, you have to work on this respiratory system as well. In contrast to the submaximal exercises, new evidence indicates that the respiratory system, respiratory muscle fatigue, may be a limiting factor in exercise performance at work rate greater than 90% of VO2 max. So that shows if you're going to train an athlete at a higher intensity exercises, then this respiratory system will be the game changer, and this will define the exercise performance of your athlete. And further, incomplete pulmonary gas exchange may occur in some athlete, endurance athlete, and limit exercise performance at high exercise intensities. So even you have worked a lot on increasing the respiratory system or respiratory efficiency, but some athlete remains inefficient in order to improve their oxygen saturation or gases exchange abilities. But this slide is just to give you another picture, but it is important that you should work on cardiovascular system and the respiratory system together to enhance the performance of an athlete. So with this slide, we conclude this chapter, and I will continue our teaching with exercise physiology, and we will have our next topic in our next lecture, and we will discuss this chapter in great depth in our interactive session. Thank you very much.